Mr. Torres,
Yes,
is it okay if I leave at 2:15 to go to another class?
of course.
Thank
Yeah,
you.
I'll record this video and then post it, um, and you'll be able to catch up or watch it later if you want. Okay?
Okay, thank you.
Sure. Okay, can everybody hear me okay? Okay, I got a yes from Gwendolyn. Thank you. We'll start at 1:30. It's almost 1:30.
Ready to connect.
All right, let's get started with this one. These worksheets are examples of problems that are similar to the problems you're working in WebAssign. And they all come out of your textbook. So remember, when you go into your textbook, you'll see lots of problems there. And the text also has solutions. It works out solutions for you. And all of the, I believe it's the odd numbered problems in your homework sections in the textbook have answers in the back of the book. You know, answers are only one part of the equation, right? How do you derive a solution? That's an integral part of learning any subject, is how do you arrive at a solution of a problem? And hopefully it matches the answer in the book, okay? These problems here are representative of each chapter that you'll go through. So in this particular worksheet, we're going to talk about probability, which is the mathematical foundation for statistics, but it's really a subject unto its own. So these problems here are just trying to get you to think about what a probability space is and how you would calculate probabilities using the notion of relative frequency. So if we have a sample space of the outcomes of an experiment, like tossing a coin, and then we define various events that are subsets of the sample space, then if we count the number of occurrences in the sample space particular to an event, then we can take the ratio of the number of such outcomes in the event A divided out by the total number of outcomes that make up the sample space. So that's the notion of relative frequency. And in the previous worksheet that we did on Friday, we actually tossed a coin 3 times. we listed all of the outcomes of the sample space, and then we can define an event exactly no heads in 3 tosses, or 2 heads in 3 tosses, or at least 1 head in 3 tosses, and then identify those outcomes, count them up, and take the ratio between the number of outcomes in the event A and the total number of outcomes in the sample space S. Okay, so let's do that over here as we go through each of these problems. So the problem reads as follows. There are 23 countries in North America. And the reason that there are so many in North America is that they're throwing in countries in the Caribbean, which are considered part of North America. Okay. And, you know, we all know about Canada and the United States, and I guess Mexico is part of North America. And then you throw in all the Caribbean countries, Haiti, the Dominican Republic, Cuba, Jamaica, and the list goes on and on, okay? 12 countries in South America, 47 countries in Europe, okay? And that again would be interesting to see what they consider to be a country in Europe. Russia might even be considered as a country in Europe. 44 countries in Asia, 54 countries in Africa, and 14 in Oceania. I don't know if I'm pronouncing that correctly. Oceania, which is the Pacific Ocean region. So we have all of these countries around the planet. So that would be our sample space, right? The list of all of the countries in the planet, and we would define an event A to be that a country belongs to Asia. E, the country belongs to Europe, and so on. Okay. All right. So as I mentioned, the probability of A, that is that if you were to select a country at random, what's the probability that it would be in Asia? Okay. Well, we're told that there are 44 countries in Asia. So we take the relative frequency, don't we? So all we do is simply take the ratio of 44 to the total number of countries. So to get the denominator in this fraction, in this relative frequency, we would have to add up all of these different values, okay? And if we did that, you can double check that, you would get a total number of 194. So the number of elements in your sample space is the number of countries in the world. That's 194. And then we can take these relative frequencies, and these turn out to be the probability of selecting a country in Asia. P of A is 44 over 194. Right? Now, one comment about relative frequencies, you can leave it as a fraction. That's perfectly correct. If you want to, you can simplify the fraction by canceling out factors which are common from top and bottom. And in this case, we could do that. We could cancel the 2, 44 becomes 22, 194 becomes 97. So either one of these two fractional descriptions of the relative frequency is correct. Or we could take it to a calculator and get a decimal approximation. And so if you type in 22/97 into your calculator and round it to 2 decimal places, you would get 0.23. Okay. All right, so we can do that with each one of these events. E is the probability that a country is in Europe, okay? And we're told that there are 47 countries in Europe. So we would take our relative frequency, 47/194, and get 0.24. All right, are there any questions about this problem? Any questions? Gwendolyn, do you see that? Okay. Gwendolyn, why is P of F equal to 54/194? F up here is Africa. So why is P of F 54/194? Gwendolyn?
There are 54 countries in Africa, and isn't 194 the total?
Yes. Okay. So 194, as Gwendolyn asked, we would have to sum up all of these values here to get our denominator, and then we would take the relative frequency. Good. Thanks, Gwendolyn. Okay, let's move into exercise 2. And here we have games of chance, as they're called. And the casino is a fun place to go. And people flock to the casino hoping to hit the jackpot. However, mathematics tells us that the probability of hitting the jackpot may be very small. And for example, in poker, the royal flush on the video machine in a casino pays, who knows, the house may set a winning of $100,000 or more. Okay, so the player is attracted to that winnings and will play the video machine in hopes of striking it rich. Okay, and mathematicians have said, well, wait a minute now, what's your probability of winning on a single trial? Let's suppose you bet a quarter. And what's the chance of winning the jackpot based on drawing a royal flush? A royal flush is the ace, king, queen, jack, and 10 of hearts. Okay? And those of you who have played poker know that even getting 2 pair, 3 of a kind, a full house, a straight, is difficult. Okay? Let alone a straight, a flush, which is a straight of all hearts, but not just any hearts, ace, king, queen, jack, and 10. So it's important that in mathematics and in statistics that we understand how these probabilities are calculated. A lot of what we study in statistics depends on these mathematical properties of random experiments. Because after all, drawing a sample is a random experiment. Okay? All right, so let's go to exercise 2A here. What is the probability of drawing a red card in a standard deck of 52 cards? Now, a standard deck, as you know, has 4 suits: aces, diamonds, clubs, and spades. And each of those 4 suits has 13 cards. If you want to count the deuce first, 2, 3, 4, all the way up to the ace. And in that sequence, there are 13 cards. So the standard deck has the 4 suits. Each suit has 14 cards. So our standard deck has 52 cards. Half of them are red, right? The hearts and the diamonds are red. So if we want to let A be the event that you draw a red card, then all we have to do is take the relative frequency of red in the deck, which is 26. Half of the cards are red. And so we take their ratio with the total number of cards in the deck, which is 52, and we get a half. So you have a probability of a half of drawing a red card, okay? And what is the probability of drawing a club? Well, there are only 13 clubs in the deck. So our numerator here is 13. Our denominator is 52. So you have a probability of 1/4 of drawing the club at random in a pick of 1 card from the standard deck, okay? And in the next problem, we've got a joint event here. What is the probability of rolling an even number of dots with a fair six-sided die numbered 1 through 6? Okay, so our event is defined by the 2, the 4, or the 6. Those are the 3 outcomes that define the event C. And then we know that the total number of outcomes, the numbers 1 through 6, is 6. So we take the ratio of 3/6 to get a half. Okay. Now for the prime numbers, what are the prime numbers? Well, in algebra, you define those to be the numbers that are only divisible by themselves in 1. They're not a composite product of primes, okay? And what you did in algebra is you actually reduced whole numbers, let's say positive integers, into a product of their primes. So this was one of the famous problems in mathematics, is showing that there are an infinite number of primes, and also showing that each positive integer has a unique prime factorization, right? So in the sequence from 1 to 6, the primes are 2, 3, and 5. Those are the elements. We exclude 1 from the list of primes. Typically, that's not our first prime. Our primes start with 2 and then go on up. As I said, there is no finite number of primes. And the proof of that fact is not trivial, but it's fairly straightforward, okay? And the way to prove that is to assume that there are a finite number of primes, take the product of all those finite primes, and then add 1. And that number there is not divisible by any of the primes that you have in your finite list, right? Okay, so there are an infinite number of primes. So we've identified the 3 primes here, 2, 3, and 5. So there are 3 elements in the event D. And so we take the ratio 3/6 to get a half. Any questions about number 2? Now to go back to the poker game, what's the probability of a royal flush? If you get a royal flush on your video machine, you win the jackpot of $100,000. It's pretty tempting, isn't it? Okay, so you insert a quarter, you press a button, and the machine gives you a hand of 5 cards. And we're crossing our fingers that we get the royal flush and walk away with $100,000. But the number of 5-card hands that you can draw out of a deck of 52 cards is quite large, okay? And that number is on your calculator. It's called NCR, for the number of combinations of taking R items out of a total of N. So let's just go ahead and calculate that on the calculator. Those of you who have a calculator like this TI-36X Pro, you can type in N. For us, N is 52. And then I'll hit the NCR key and type in 5. And here's what we get. The number of 5-card hands out of a deck of 52 cards is 2,598,960. Okay? So it's not quite 3 million. It's about 260,000. So your odds of winning the jackpot is 1 in about 260,000. Okay? Pretty small odds, right? So, but you know, for a quarter, why not? Okay? And if I lose the first trial, I'll try it again, and so on. So that's how the house gets rich, because they know that the odds of winning the jackpot are very small indeed. So that's how gambling works. But we're having a lot of fun losing our quarters, right? Okay. All right. So in number 3, here we have another game of chance, let's call it, where we take a special deck of cards. This deck has only 10 cards in it. 4 are green, 3 are blue, and the other 3 are red. Okay, so the deck has these characteristics. And we're going to pick a card at random. And so we'll pick a card, and then we'll toss a coin. So here we have this bilateral experiment, right? We're doing 2 things. We're drawing a card, and then we're tossing the coin. Now, let's look at the solution here for the sample space. Remember, in these experiments, if we can list the sample space and count the number of elements in the sample space, then we have the denominator of our relative frequency. Okay? And then if we define the experiment in this way, we can count up the number of elements in the event and take the ratio or the relative frequency to get our probability. So let's first list the sample space. And we'll do it in the following way. We'll write out an ordered pair where the first element in the ordered pair is the card selected at random. And then we'll toss the coin, and that comes up heads or tails. Okay. So let's go ahead and list them. We can choose the green card first and then come up with a heads on the toss. Or we can come up with a tails on the toss, having selected a green card. Similarly, blue and red. Blue card, then a heads. Blue card, then a tails. Red card, then a heads. Red card, then a tails. So your algebra set notation gives us a very nice way of writing down the sample space as a set of outcomes in this bilateral experiment here, right? And notice there are 6 elements here, 3 colors in the deck, 2 outcomes in the toss of the coin, so 3 times 2 gives us 6. And this set notation here you saw in your algebra classes, and it gives you a very nice way of denoting the sample space. Okay. Let A be the event that a blue card is picked first, followed by landing a head on the coin toss. Find the probability of A. Now, there's something fairly important going on here, and that is that the selection of the card is independent of the toss of the coin. That is, the probabilities of these 2 separate pieces don't influence each other. The fact that I picked a color of a certain type in the draw of the card has no bearing on whether the coin appears as a heads or a tails. So those 2 events, sub-events, are called independent. We'll come to that in the next problem. So by the multiplicative rule of probability, when 2 events, excuse me, are independent, then the probability of their joint occurrence is the product of their probabilities of the single occurrence. So let's use that rule here. So the probability of A is select a blue card first, followed up by a head, that's A. And since the 2 events, these 2 sub-events are independent, we simply multiply by the probability of the blue. Since there are 3 out of 10 blue cards in the deck, that probability is 3/10. And then, as we know, the probability of heads is 1/2. So those 2 multiply using the multiplicative rule, and we get 3/20, right? Now, the multiplicative rule from your text, as you know, is defined in terms of conditional probability. That is, the probability of A and B turns out to be the conditional probability of P given B over the probability of B. All right? And we'll see that in the next problem. Okay? And when 2 events are independent, their conditional probability does not depend on the probability on the event that you're conditioning. So the probability of A given B is equal to the probability of A if the 2 events are independent. That is, B has no influence on the outcome A. All right. Now, mutually exclusive means that the 2 sets that define the events have no elements in common. One clear example of 2 mutually exclusive events are the events A and the complement of A, which is denoted in your text by A prime. So here you have 2 events. Something happens, something doesn't happen. Okay, so those 2 events are mutually exclusive because they're complementary. Okay, so that's one obvious example of 2 events that are mutually exclusive, A and not A. Okay. All right, now B again is our event that a red or green is picked, followed by landing ahead. Now A is the event that a blue card is picked. All right, so A and B are mutually exclusive because you can't have the joint occurrence of blue and red or green. Those are mutually exclusive. Okay. And therefore, the probability that they happen jointly is 0. They can't happen jointly. Either one or the other happens, but not both, okay? Now, C is the event that a red or blue is picked. Remember, A is the event that blue is picked, so those two do have an intersection, which is non-empty, okay? So you can pick blue and then toss a heads and satisfy C. And if you pick a blue and toss a heads, you've satisfied A. So they have two outcomes in common. So they're not mutually exclusive. All right. All right. Okay. All right, so there we have number 3. Any questions about number 3? All right, let's go to the next one here. And here we're given a scenario involving events C and D. So let's consider the scenario where it's assumed that the probability of C is 0.4. The probability of D is 0.5. The probability of C given D, that is the conditional probability of observing C, if you've already observed D, that's going to be 0.6. Okay? All right? So we're told that D does have some influence on the event C. The event C by itself just has a probability of 0.4. But if you condition on D, then the probability of C actually goes up to 0.6. So they're not independent. D does have some influence on the probability of C when you condition on D. All right. So let's first find the probability of C and D. And here is the multiplicative property. So the probability of C and D is the probability of D times the probability of C given D. That's a theorem or a fact in probability theory. It's called the multiplicative rule. And of course, it's described in great detail in your textbook. Okay. So when we factor using the multiplicative rule, now we can substitute from the scenario what these factors are on the right. Probability of D is given to us to be 0.5, and the probability of C given D is given to us in the scenario to be 0.6. And when we multiply these two probabilities together, we get 0.3. So the probability of the joint occurrence of C and D under this scenario is 3/10. Okay. And remember that if two events are mutually exclusive, then the probability of their intersection would be 0. But this is not the case with C and D. The probability of C and D is 0.3, which is clearly not 0, so they're not mutually exclusive. Okay? And we know that they're not independent because D influences C, that is the probability of C given D, we're given that to be 0.6. The probability of C is 0.4, so they're not independent. Okay. And then to calculate the probability of C or D, we use the so-called additive rule of probability. The additive rule says that the probability of C or D is the sum of their probabilities minus the probability of their intersection or their joint occurrence, the probability of C and D. Again, that's a theorem. That's a law or a rule in probability called the additive rule. So we have all of these different parts here from the scenario and what we calculated in part A. So the probability of C is 0.4, the probability of D is 0.5, and we calculated the probability of their intersection to be 0.3, and when we apply the rule, we get 0.4 plus 0.4 minus 0.3, and that gives us 0.6. Okay. All right. And we can do the same thing with the conditional probability of D given C. Okay. Notice that if you reverse in part A here, where I've listed the rule, if you reverse the role of C and D, now you want the probability of D given C, okay? It's, again, probability of C and D divided by the probability of C. This is actually the definition of conditional probability, okay? To calculate the probability of D given C, you divide the probability of their intersection by the probability C, the event that you're conditioning on. And we have the probability of C and D from part A, which is 0.3, and we divide by the probability of C. We know probability of C is given to be 0.4, so this ratio then is 0.75. Okay. Some of you have already done these problems in WebAssign using the additive rule or the multiplicative rule. Okay. And some of these problems will appear on your midterm. So if you haven't done WebAssign yet, you need to get in there and do some of those problems, if not all of them, in preparation for your midterm. Make sure that you can use these rules with facility in order to solve problems like this. And as I said, some of you have already done this in WebAssign. Okay, let's move down to the last problem now. Okay. And here we have another special deck of cards. The deck is a 10-card deck consisting of 6 green cards and 4 yellow cards. You're going to draw 2 cards at random without replacement. So for example, if I draw a green card on my first draw, I'm not going to replace that. I'm going to set it aside. That reduces the deck on my second draw to 9 cards, right? We've taken 1 green card out of there, set it aside, and now we draw again from the remaining 9 cards, 5 of which are green, and 4 of which are yellow. So there's a conditional probability going on, okay? What's the probability of an event given that I draw a green card on the first draw. Okay. All right, now let's draw a tree diagram of this problem. Well, what is a tree diagram? Okay. A tree diagram is a way for us to map out all of the outcomes in this draw of 2 cards from this deck. Remember, we're drawing without replacement. We have a probability of 6/10 of drawing the green card first, and a probability of 4/10 of drawing the yellow card first. And I've denoted that here in the tree. So if we start out here, we either draw green, and then we can draw green or yellow on the second draw. So those are the branches out here. And then the bottom branch is if you were to draw a yellow card first, and then follow that up with a second draw, which might be green or yellow, right? Okay. So if we go along the top path of the tree, the top branch of the tree, we don't replace the green card that we drew. And now we have probability 5/9, as I mentioned, of drawing the green card on the second draw, and a probability of 4/9. Why 4? Well, because in the first draw you drew the green. That doesn't disturb the 4 remaining yellow cards, but it does reduce the number of cards in your deck by 1 from 10 to 9, and so your probability of drawing the yellow on the second draw is 4/9. Okay. Similarly, down here in this lower branch, if you start out with a yellow draw, then on your second draw, you've got the full complement of green. So the probability of green on the second draw would be 6/9. But you only have 3 yellows left now in the deck, since you've already drawn a yellow and haven't replaced, you would get 3/9. Okay? So what is the probability of drawing green on the first draw, followed by another green? Okay? Well, we see it up here. It's the probability of drawing the green times the probability of drawing the green on the second card, given that you drew a green on the first card, on the first draw. So here it's right here. It's using the multiplicative property. You get the probability of green on the second draw, given that you drew it on the first draw, times the probability of green on the first draw. So we get the 5/9, all right, which is this probability here, G2 given G1, times the probability of green on the first card, which is 6/10, and that product is 30/90, which you can rewrite in simplified form as 1/3. Okay. Now, I'm not a stickler for simplified fractions. In your algebra class, you spend a lot of time simplifying fractions, right? Finding common factors and canceling them out and getting a nice reduced fraction, right? But in probability theory, you can leave it as a non-reduced fraction, or you can simplify it. You know, we mathematicians, we like to simplify things, so typically we simplify them, but it's not necessary. It's still correct, okay? All right, now let's try the next one. The probability of at least one green in the 2 draws, okay? So what you could do is you could go on this tree calculate the probability of getting at least one green. So how would that work? You could get the 2 green cards in the 2 draws, right? That's at least 1 green. Or you could get a green on the first draw and a yellow on the second draw, or vice versa, a yellow and then a green. In any one of those scenarios, you would have drawn at least 1 green card. And then you could add those probabilities up. All 3 of those events are mutually exclusive, so their probabilities simply add up. Or let's do it a different way. What's the complement of at least 1 green card? Okay. Well, if they're both yellow, right, you don't get at least 1 green card, right? So what if we calculate the probability that they're both yellow, which is this branch down here. And then we know that the probability of A prime is 1 minus the probability of A. Remember, either A or its complement must happen. So the sum of their probabilities is 1. Again, that fact is given to you in your textbook. So let's define the complement, which is that they're both yellow, and then we'll calculate the probability that they're both yellow, subtract that from 1, and that'll give us the probability of at least 1 green. So the probability that they're both yellow is 4/10 times 3/9, right? By the multiplicative rule. Draw your yellow card first, and then follow that up with another draw of the yellow card. And we see that that's 4/10 times 3/9. Okay? And then at least 1 green is the complement of that. So we're going to subtract that product from 1 to get the 13/15. Right? And as I said earlier, you could go ahead and define all of the ways that you get at least 1 green card and add up those probabilities, and you'll get the same value. Okay, but this is kind of neat. It's not a trick. It's just applying the rules of probability. The probability of A prime plus the probability of A is always 1. Now, what's the probability of G2 given G1? Well, that's up here, right? That's just 5/9. Given that you saw the green card first, what's the probability of getting a green card on the second draw? That's the conditional probability, and that's just 5/9, right? Are G1 and G2 independent? Your intuition says no, because I'm not replacing the green card, it'll have an effect on the probability of a green card on the second draw. Okay, and okay, so they're not independent, of course, all right, because their conditional probability is certainly not equal to G2, right? We saw that up here, okay? All right, and so this calculation down here basically goes through that reasoning and shows you that probability G2 given G1, which is 5/9, is not the probability of G2. Probability of G2 turns out to be 3/5. Okay, so there you have a contradiction if you assume that they were independent, so that they're not independent. Okay, any questions about any of these 5 exercises here? And remember, these exercises, some of these exercises like this will appear on your midterm. So make sure that you follow all of the logic here in each of these solutions and go back into your textbook or complete your WebAssign homework in your probability chapter and make sure that you build up your skills in applying these formulas, and you can calculate these probabilities. Okay. All right, guys, that's it. Let's adjourn the meeting if there aren't any questions. I don't see any chats here, so we're all good there. Okay, and we'll march on, and on Friday, we'll have another short session on the next worksheet. Okay. All right, guys. Thank you for joining the meeting, and I'll end it now. Any last questions? Going once? Going twice? Okay, see you on Friday. Bye now.